Hello class, this is chapter 1 for section 1.3, problem solving and critical thinking. We are going to be looking specifically today at problem solving. Let me get my marker ready. Alright, so our objective is to solve problems using the organization of the 4-step problem solving process. Poya's 4 steps in problem solving. Step 1 is to understand the problem. The way to do this is to read the problem several times. The first reading can serve as an overview, and in the second reading we can write down what information is given and determine exactly what the problem requires you to find. Step 2, we are going to devise a plan. The plan for solving the problem might involve one or more of these problem-solving strategies. We could use inductive reasoning to look for a pattern. We could make a systematic list or table. We could use estimation to make an educated guess at the solution. We could check the guess against the problem's conditions and work backwards to eventually determine the solution. Or we could try expressing the problem more simply and solve a similar but simpler problem. We could also use trial and error. Now, we want to list the given information in a continued chart or table, try to make a step or a sketch or a diagram to illustrate the problem. We want to relate the problem to similar problems that you have seen before, try applying the procedures you've used to solve similar problems to the new problem. We could look for a catch if the answer seems too obvious. Perhaps the problem involves some sort of trick question deliberately intended to lead the problem solver in the wrong direction. We could use the given information to eliminate some possibilities, and we can also use common sense. Now in step 3, we want to carry out whatever plan we decided on so that we can try and solve the problem. Step 4, we want to look back and check that answer we got. The answer should satisfy the conditions of the problem, all of the conditions. The answer should make sense and be reasonable. If this is not the case, we need to recheck the method and any calculations that we have made in the problem. Perhaps there is an alternative way to arrive at a correct solution. So let's look at example 1 and see if we can find what is missing. What necessary piece of information is missing and prevents you from solving the following problem? The problem is, a man purchased 5 shirts, each at the same discount price. How much did he pay for them? Solution. Step 1, we need to understand this problem. Here's what's given. The number of shirts purchased is 5. We must find out how much the man paid for the 5 shirts. Because the man purchased 5 shirts, they were each at the same discount price, and we want to know how much he paid for them. We understand that problem. Step 2, we need to devise a plan. The amount the man paid for the 5 shirts is the number of shirts 5 times the cost of the shirt. The discount price of each shirt is not given. The missing piece of information that makes this problem impossible to solve So if we go back and we're looking at this, if you didn't catch it, the discount price of the shirt is what's not given. That is the missing information that makes this problem impossible to solve. So this is essentially your answer to this problem. We need this discounted price in order to figure out how much he paid for the shirts or for each shirt, if that makes sense. Without the discounted price for the shirts, we can't figure out what he paid for the shirts. We know he had 5 shirts, but hey, that doesn't matter if we don't know what he paid for even at least 1 or all 5 altogether. That is the missing piece. So that is the answer. Now, let's look at this next example. It says, by paying $100 cash up front and the balance at $20 a week, how long will it take to pay for a bicycle costing $680? Now we're going to use the 4-step program here as well. We're going to look and understand the problem first. So in order to do so, we can write out what the problem gives us. Okay, so it gives us the cost of the bicycle. That is $680. It also tells us this amount that we have already paid in cash and the amount that we plan to make weekly payments with. So this is the basis of the information we need from this word problem in order to solve it. We're going to devise a plan to solve this problem. We're going to subtract the amount paid in cash from the cost of the bicycle. This will result in the balance that still needs to be paid for this bicycle. We will divide this result by the weekly payment of $20 to find the number of weeks required to pay for said bicycle. Now step 3, we're going to carry out this plan that we have laid out between steps 1 and 2. So we got the information in step 1. We're going to devise the plan in step 2. Step 3 is to carry out that plan that we devised based on that information. So let's begin by finding this initial balance. Okay, we knew that the bicycle cost $680. We already put $100 down on it, so we should only owe $580. And that's exactly what we see here. Okay, we had 680 bucks that the bicycle cost. We paid the $100 on it. We still owe 580 bucks. Now, with that $580, in order to determine the number of weeks that we're going to pay for it, all we have to do is divide that 580 by 20, because $20 is what we are paying per week. Now, when we do that, you can use a calculator if you like, but try it by hand. Let's get some of this hand practice in here. When we do that, we're going to see that 20 doesn't go into 5, but 20 does go into 58. 20 goes into 58 2 times. 20 times 2 is 40. 58 minus 40 is 180, because I'm going to drop this 0 here. So 58 minus 40 is 18, add the 0, so 180. Now, 20 times 9 is going to give you 180. 180 minus 180 is 0, so we should see it should take us 29 weeks in order to pay this off. So it says now we're going to divide the balance by $20, the weekly payment, to find the number of weeks. 580 divided by 20 equals 29 weeks, which is exactly what we found when we did our math. Now, just because we have an answer doesn't mean that it's necessarily correct. This is why we include step 4. We want to look back and check the answer we got. We can double check this arithmetic. We can also see if the answer satisfies the conditions of the problem. Let's look at $20 for a weekly payment times the 29 weeks that we're going to pay that. That will multiply to give us 580. If you don't believe me, let's do it over here to the side, just so you can see it actually multiplied. So we'll do 20 times 29. You could check this on a calculator if you'd like. But 9 times 0 is 0. 9 times 2 is 18. I'm going to drop a 0. 2 times 0 is 0. 2 times 2 is 4. 0 and 0 is 0. 8 and 0 is 8. 4 and 1 is 5. So indeed, this multiplication does give us the 580 for the weekly payments. Now we also have to add back that $100 that we paid initially. So we could do that. If we add that, we see that that's $680, which is the total cost of the bicycle. So essentially, we just work backwards to prove that the answer we got of 29 weeks is indeed correct. So the answer of 29 weeks satisfies the condition that the cost of the bicycle is $680. All right, example 4. It says, suppose you are an engineer programming the automatic gate for a 50-cent toll. The gate accepts exact change only. It does not accept pennies. How many coin combinations must you program the gate to accept? All right, for this solution, we really have to understand the problem. We know that the total change must always be 50 cents. We need to find all combinations using half dollars, quarters, dimes, and nickels. We cannot use pennies. The machine does not accept pennies. So we need to look at all combinations of half dollars, quarters, dimes, and nickels that we could use in order to make 50 cents, and 50 cents exactly, because the machine only accepts exact change. So we needed to devise a plan to figure this out. We really need to make a list of all possible coin combinations. We will do this beginning with the coins of larger value and work towards the coins of smaller value. That will be the easiest way to do this problem. This can seem like a daunting task, but if you take it piece by piece, it's really not that bad. Step 3, we're going to carry out our plan to solve this problem. We're going to set up a table, is what we're going to do. And in this table, we are going to use half dollars, quarters, dimes, nickels as the table headings, and we're going to count the coin combinations in the table. So, if you were to do that, I have a professional looking table here, but you could sketch this out on a piece of notebook paper, no problem. One of your headings here would be half dollars, the other would be quarters, the other would be dimes, and the last would be nickels. And what we would see is a half dollar is 50 cents all by itself. There's no other type of coin that we need to add to it to be that 50 cents. So the only option for using half dollars is to use one half dollar, and we have paid the toll and need no other coins to add to it. Then we'll work our way down the list. Okay, that's the only thing I can use for half dollars. Just one half dollar covers it, so my half dollar column is actually done now. If I look at quarters, if I use 2 quarters, I'll have 50 cents. I'm done here. But if I use 1 quarter, how many dimes would it take to kind of make me towards that 50 cents goal? It would take me 1 quarter, 2 dimes, that would be 45 cents. And then I'd also need a nickel here to make that 45 cents 50 cents. You're like, okay, well, what if I used 1 quarter and then just 1 dime? That would give me 35 cents. What would I need in nickels to make up the remaining? Well, 35 cents, I would need, go by fives, that would be 40, 45, 50. I would need 3 nickels to make up the difference. So that 1 quarter, 1 dime, and 3 nickels would make up my 50 cents. Now, if I use 1 quarter, no dimes, and just nickels here, then I'm looking at 25 cents with the quarter, and then I have to make up the rest with nickels. So I'm looking at 25 cents, and then I'm going to need 5 nickels to make 25 more cents so that I can have my 50 cents overall. Now, if I use no quarters, so I'm done using quarters. I've zeroed those out. I've done all possible combinations with quarters at this point. And I just look at using dimes. Dimes are 10 cents. So 5 dimes would make 50 cents. And I wouldn't need any nickels. Just kind of working down here. So if I used 4 dimes, 4 dimes is 40 cents. I would need 2 nickels to make up the difference, because 2 nickels would be an additional 10 cents. So 40 cents plus 10 would be our 50 cents we needed. If I only used 3, you see we're basically counting down. 3 dimes would be 30 cents, which means I would need to make up the 20-cent difference in nickels, and that's why I would have 4 nickels. 2 dimes, I would need 6 nickels. 1 dime, I would need 8, because 1 dime is 10 cents, 8 nickels is 40 cents, 10 cents plus 40 cents is 50 cents. And if I use no nickels, no quarters, or no half dollars and tried to make it all up in nickels, I would need 10, because 10 times 5 cents is 50 cents. So you can see we basically did a elimination kind of method as we worked down our table. We started with half dollars, we went through quarters until we did all possible combinations of 1 quarter down to no quarters. Same thing with dimes. We did all possible combination of dimes here, 5, 4, 3, 2, 1, 0, until we had no dimes left here, which left us with all nickels. So it showed us essentially that the number of combinations that we need, each one of these rows here makes up a combination of coins. We've got 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like 11 possible combinations here of coins that could make up 50 cents that we need to program. Okay, so let's look back and check this answer. In order to double check and make sure you have all possible combinations and that they add up to 50 cents, double check your total count. Okay, we essentially did that. We worked all the way through our table. Everything added up to 50 cents. It took us 11 combinations in order to get all of those combinations that need to be programmed, right? So the actual answer back here to our problem, this is how many coin combinations must you program the gate to accept. You need to program 11. That would be our actual answer to our initial problem. All right, example 5 says let's use a diagram. We have 4 runners. They are in a 1-mile race. Maria, Athrea, Thelma, and Debbie. Points are awarded only to the women finishing first or second. The first place winner gets more points than the second place winner. That makes sense. How many different arrangements of first and second place winners are possible? Okay. Let's understand the problem. There are 3 possibilities for first and second position. Okay. So, if we look at this, let's say, for instance, that Maria takes first place. Okay, if Maria, because there are 4 friends here, there are Maria, Arthrea, I'm probably saying that name wrong, Thelma, and Debbie. We got 4 friends overall. Okay, so if one of them takes first place, Maria in this case, that means there's 3 possible combinations for second place. So, possibilities for first and second place. Maria, Arthrea, Maria, Thelma, and Maria, Debbie. That's if Maria comes first, right? Now, note that Maria finishing first and Arthrea finishing second is a different outcome from Arthrea finishing first and Maria finishing second, since first place obviously gets more points than second place. So, what we need to do, instead of just making one chart here, we have to make it for each possibility of first place as well. So we have to look at the possibility that Maria got first place and then one of her 3 friends got second, which gives us 3 combinations. We have to look at Arthrea getting first place and one of her 3 friends getting second place, which gives us 3 more combinations. And then we look at Thelma, and then we look at Debbie, and each of those also gives 3 additional combinations here. So listing each woman as first place winner and pairing her with each of her 3 other women results in a tree diagram here. And the final column shows all possible combinations. Okay. What we notice here is that if we add all those combinations up, 3, 6, 9, 12, we have 12 possible combinations here. So we look back and we want to check this answer. And we want to confirm that the 12 possible combinations are indeed correct. So let's check the tree diagram to make sure that there are no possible first and second place outcomes that have been left out. And then we want to double check our count for the winning pairs of runners. Okay, if we do that, we're essentially checking this last column over here. You cannot come up with any combination that hasn't already been listed here. You could try. That's the goal, is to try to think of a combination that isn't here that should be. But we have successfully come up with all combinations. So 12 is indeed our answer. This has been Chapter 1.3. Please go on your My Math Lab and begin working on your homework. If you have any questions whatsoever, please don't hesitate to reach out for additional help. Y'all have a good afternoon.